topic for consideration this evening is physical activity during growth and development. It's a longitudinal perspective. Okay? The objectives are to discuss a longitudinal study in terms of body size, maturation, shape and body composition in active and controlled boys during adolescence. It's a summary really of some of the procedures and results from a 5-year longitudinal study that we did a few years ago. Now for revision now, we're going to have a quick word on types of study. There are 2 types of study as you're aware of. One is cross-sectional and the other longitudinal. In cross-sectional studies, groups or individuals are measured at one point in time only. One point in time only. The advantages are that they're relatively cheap, they can accommodate large groups, and they can be carried out reasonably quickly. The disadvantages are that the measurements can't reveal anything about future development. They can only express what the position was at the time the measurements were taken. Okay. Now the term longitudinal means to follow on. Okay, so pure longitudinal studies refer to individuals who are measured at specifically defined times, for example, 3, 6 or 12 months over a period of several years. Okay. And all subjects are measured on all occasions. That's why it's called pure. Mixed longitudinal studies are those where some, but not all individuals have been measured. Some children may be missing for various reasons. They may be ill or changed school or left the district. But in the end, most studies become mixed longitudinal studies anyway. So in a sense, nothing is lost. Prospective studies are those where individuals are expected to be measured at these specific times in the future. Now in terms of advantages generally, the main advantage of a longitudinal study is the investigation of change. And the results will tell you about changes in the growth of individuals, for example, the degree or of normality or abnormality, or early or late maturity, and the presence and timing of specific events, such as the mid-growth spurt and the pubertal spurt, the adolescent spurt. Okay? The main disadvantage is attrition, where individuals are lost to the study. And this can be a problem if sample sizes are small. So it's useful to have included more individuals in your sample than were actually required. Longitudinal data are very awkward to handle, and they're very awkward to handle statistically. So you need a good statistician. That would be probably one of my first kind of consultations. Okay? It's very time consuming and requires careful administration. This is the first or the oldest longitudinal study on record. It was carried out by a Frenchman, Count de Montbellier, on his son from birth to maturity. What we've got is, this is the distance curve. We've got height in centimetres and chronological age there. And that's the distance curve, height against age. Okay. And in the bottom curve we've got velocity, the rate of growth against age, and as someone grows, of course, the rate at which they grow declines. So you get a drop before you come to the adolescent spurt there. And that's what we're interested in at the moment, peak height velocity. I'll come back to that. Now, de Montbellier was a wealthy landowner, a lawyer, and a philosopher of science. And in the interest of science, Buffon, his friend, and his colleague asked him if he would measure his son from birth to maturity. There was no indication how the measurements would be taken, except that they were taken in bare feet for every 6 months until final height had been attained. Now, the original data for this study was found by Scanlon, an American. He converted the data from the French into the metric system, and he plotted the distance curve. And that was in 1927. The velocity curve wasn't plotted until 1942. It was plotted by Darcy Wentworth-Thompson in his famous book on growth and fall. So the data went missing for a number of years. Okay. Now, de Montbellier's son was a tall child, even by today's standards, 190 centimetres, 6'3", which places him on the 97th centile of height standards in the UK. So he was quite tall. Now the distance curve is characteristic of a normal distance curve. It hasn't been smoothed in any way. It was measured every 6 months, and very probably they've joined each point together with some kind of straight edge. But considering that was done in the middle of the 18th century, then it's a remarkable presentation for a distance curve. If we look at the velocity curve, there are two main points to come from that. One is the age at which peak height velocity occurs. This is the velocity spurt. Okay? So if you go to the peak of that and drop a perpendicular, it occurs at 14.3 years. So that's the age at which the peak height velocity occurs. It's an important definition. And the value of that is 12 centimetres per year. Now both those values are consistent with values that we get today. This is another important contribution. This is the alignment of data growth curves on peak height velocity. This was done by Franz Boas. Now Franz Boas was a physical anthropologist. He was interested in language, he was interested in folklore, but he was also interested in the physical growth and development of the child. And one day Boas was calculating his velocity curves for his youngsters and noticed that the shape of the curve, the mean value of the velocity curves, was markedly different from those of the individual curves themselves. So if you look at the top curve, for example, we've got rate of growth there. That's the individual velocity curve, and there are 5 of those, okay? And if you found the average value at each chronological age, that's the shape of the mean curve that you would get. Now there's no way that mean curve represents either the shape or the value or the shape of individual curves. They're entirely different. And it was this that was troubling. So what he did therefore, after just a little bit of thought, was that he aligned all individual curves according to the point of their maximal velocity. And then he calculated the averages at each year. And now the mean curve now represents individual curves more satisfactorily and more accurately, which is more important, than it did previously. So if you look at the bottom of we've got height in centimetres, yeah? And this is called years from peak height velocity. You can see now that all those individual curves, there are just 5 of them, have been aligned according to their peak value. If you drop a perpendicular down there, you come to what is now called peak velocity or peak height velocity. Although Franz Boas called it maximal growth age. Now why it was changed, I don't know. But it's now called peak height velocity. And once you've calculated the average values at each year from peak height velocity, that's the shape of the average curve. So you can see now that the average curve represents the shape of the individual velocity curves. Okay. So what has happened really is that this has been changed from a chronological age to an age called years from peak height velocity. What it is really now is a biological age, a maturational age. You're referring to maturation and not chronology. It's not chronological time that we're interested in. Okay? So that was an important consideration. It is in effect a maturational age base, and the present study has used that principle throughout and aligned all the distance curves and the velocity curves according to years before and after peak height velocity. So that's what we've got. That's why I've shown you those two, distance and velocity and that curve, because we have that. We have those principles in our study. And this is the study that we did, the Kincoid longitudinal study. This is the sampling frame and the ethical approval. Multi-stage sampling was used to design the study. All schools in the Kincoid area were included in the sampling frame. Now there aren't many schools in the Kincoid area, so it wasn't a large sampling frame. Okay? But we had to select 3 schools from the sampling frame. Now the experimental group were active boys, they were association football players, they played for the school and they played for teams outside the school. And the control group were boys who were recreationally active, but not active in a physical sense, in a competitive sense. Okay? Nonetheless, they all participated in physical activities in school. Three schools were selected at random. One was the Lady Mary, which is now a housing estate over there. The other one is Cardiff High, down by the lake. And the other one is Longitudinal, which is behind us here at the university. And so we sent a letter to the head of each school outlining the purpose of the study, the measurements to be taken, how they would be taken, how long the study would take, and so on and so on. Okay. We started with year 1 when they came in at the age of 12. And we measured children annually, because that's all the time we had available anyway. We measured them annually until all measurements had been obtained. And that took us to 16 plus years. Because if we were after the adolescent spout, the only way we could realise how we'd obtain that was to get to it and have a value which turned over and became smaller on its way down. So we sometimes went beyond 16 years of age. And then we asked the head of school then for his approval to write to parents to allow their children to participate in the study. And the letter was sent to parents, gave all the necessary details associated with the study, and parents and children were asked to sign the consent form confirming that their child was willing to participate in the study to its conclusion. Those are some key words as well, to its conclusion, because we didn't want to lose anybody at all. This is the recruitment of subjects. Okay? Now, sample size was determined statistically, and it used the coefficient of the variation of the mean, together with some pilot data that we'd obtained for oxygen uptake for a small sample of 13-year-old boys. All we wanted was a standard deviation and a mean value were required to transpose the relevant formula which we had, so that we could transform it and find a sample suitable for our study. Okay? And for a single school with a coefficient of variation of 5%, a sample size of n equals 12 was necessary to identify differences between groups. So it was decided then to send letters of invitation to parents in all 3 schools. Cardiff High School, we invited 12, 11 accepted, 1 refused. Longitudinal High School, 16 were invited, 13 accepted, 3 refused. And Lady Mary High School, we invited 12, 9 accepted, and 3 refused. So in the experimental group, we invited a total of 40 boys, 33 accepted and 7 refused. And that's a 20% refusal rate. And in the control group, we invited 20 boys, 16 accepted, 4 refused. That too was a 20% refusal rate. We didn't ask them why they refused, although some did provide some response to that, but it wasn't necessary for them to say why. So we finished up having an experimental group of n equals 33 and a control group of n equals 16. I apologise for this slide. I'm not going to go through it. I'm just going to give you a paragraph about it. The importance of this paragraph is identifying quite specifically the point at peak height velocity, because that's our focal point in our maturational age base. Everything's based on years before and after peak height velocity. We get that wrong and we get everything wrong. So we were looking specifically to identify the age at which peak height velocity occurred and its value. So the increments for height in centimetres per year were calculated and plotted against chronological age for each individual, active and control groups. And the curves were fitted to the data using a flexible lead spline. We fitted a spline to the point, drew it, and see what the curve was like. What we were looking at was the shape of the curve, to see what the shape of the curve was like. Was it Gaussian? Was it screwed one way or screwed the other way? And exactly where was it? What was its shape? Was it peaked or was it flat? So it was an explorative process. And we recorded the mean and the value, mean age and value at peak height velocity were recorded for the active and the control groups. And then the adolescent spurt was scanned using third-degree polynomials. Those were to identify the age and value at peak height velocity, and a comparison was also made between active and control groups. And finally, of course, we had then to make a comparison between the incremental and the polynomial groups. And the differences in the age between incremental and polynomial groups were minor. In the active and control group, the differences in polynomial and the other incremental group were 0.04 of a year. That was the only difference there was, a decimal point of a year between the incremental method and the polynomial method. So you can see, in a sense, how reliable fitting a curve to data can be. And then some people still believe in doing it that way, because it provides a good degree of accuracy. So in conclusion, the use of cubic polynomials was formally accepted simply because it was easier for us to identify the maximal age and the maximal value of peak height velocity for both groups. And all distance and all velocity curves were analysed in this manner, and data aligned according to years before and after peak height velocity. So, this now is a couple of measurements that we took just to illustrate. This is height, a seemingly simple measure, but very often incorrectly carried out. Surprisingly, the extent to which the figures are right or wrong, usually wrong. Okay. The heels should be kept on the ground, and the buttocks and the scapula in contact with the backbone, and head in the Frankfurt plane, and then you can bring the headboard down onto the head. If you ask the subject then, stretch up, a bit more, a bit more. You'll get a centimetre at least on top of it, up of that, to increase his height. It's just the diurnal effect that happens during the course of the day. Okay? And the measurer puts his hands under the mastoid processes and just stretches him up there a little bit more, so you can get a couple of more centimetres from it. Okay? So that's the best way to measure height and get a good dimension. Okay? And the technical error measurement for stature when we were doing this was 1 to 2 millimetres. So you should be able to measure to at least 2 millimetres for height. Another lengths we measured were sitting height and leg length. Skeletal measurements, we measured shoulder diameter, hip diameter, bicondylar diameters of the elbow and the knee, and these widths were used primarily for the mesomorphic component of the anthropometric somatottype. And the skin fold thicknesses and circumferences, skin folds were used for a variety of purposes. We measured at the biceps, the triceps, the subscapular, suprailiac, mid-thigh and medial calf. And circumferences included the arm circumference and the calf. Now you'll notice that measurements here are being taken on the left-hand side of the body. Now there are some institutions and some organisations and some national institutions, one which I belong to myself, who suggest that subcutaneous tissue should be measured on the right-hand side of the body. The number of people I know who've taken measurements on the left and measurements on the right and found no differences at all are numerous. There is simply no difference between skin fold thicknesses on the left and skin fold thicknesses on the right. If you measure the circumference, there may well be because you use this arm more than you use this arm. But that's the only reason why. So you have to play it as it comes. If they want it on the right, you do it on the right. If they want it on the left, you do it on the left. These are now then the distance and velocity curves for height. Now, all height and height velocities are plotted on the y-axis, the vertical axis. Okay? Height in centimetres and velocity in centimetres per year. Okay? The control group was taller. This is the control group in black. The control group was taller than the active group up to about plus 1 year peak height velocity. This is our years from peak height velocity now. It's not a chronological age. You could work chronological age out from it. This point now, peak height velocity is 14.2. That's how it came out. That's what it was. 14.2. The value for the UK is 14.1. So we can't have done it all wrong. 14.2, we found peak height velocity. Okay? So the sedentary group is larger than the active group, up to about plus 1 year peak height velocity, which is 170 centimetres, about. Okay? And you'll also notice that the active group, the rate of the active group, is much greater than the sedentary group before it crosses over and becomes finally higher. There's no significant difference at all between the control and the active groups. Now, by convention, velocities are plotted at the midpoint in all cases. If you measure somebody at 10 and you measure somebody at 11 and you work out the velocity, the rate of growth per year, it is plotted on the velocity curve at the midpoint, 10.5. And not 10 and not 11, 10.5. That's where it's plotted. Okay? So if you look at the velocity now, okay, so the active curve, the reason the active curve is taller is because of the larger velocities in the velocity group. The active group have much larger velocities, and so therefore you will become taller. Okay? If you look at the velocity now, at plus 0.1, at plus 0.1 is where the active group becomes larger than the control group. So it's the velocity itself which is responsible for the shape of the curve. And that's true in all positions, as you'll see. If you look at body mass, okay, the control group is slightly larger in the sedentary group than the active group, again, up to about minus 0.5 years from peak height velocity. And it's due to the greater velocity in the control group than the active group. It's the reason for that difference. Okay? So from that point on, you get an increase in height, which is due to the larger active velocities for height, for weight. Okay? It's significant at plus 1 year, which is about 56 kilograms, something of that order. And if you look at the velocity again, at minus 0.5, at minus 0.5, again, is the point where the active group crosses over the sedentary group and becomes larger. So you can see how important the velocities are. If you get your measurements wrong, you'll get your velocities wrong. And if you get your velocities wrong, then your shape will be wrong. This is maturation now, biological maturation. That is how far an individual has progressed towards physiological maturity. Maturation measurement or concept, even the concept of it, needs to have endpoints which are the same in all individuals, so that maturity can be expressed on a kind of an even playing field. And in the latest series, the TW3 series, they use 0 to 1000. 0 being immature and 1000 being mature. Okay. So height and other size measurements can't be used to measure maturation because the end point is different in different individuals. Okay. However, the bones of the hand and the wrist provide a suitable sequence of events for this purpose. So that we have, therefore, skeletal maturity, and that should be used wherever possible. These three boys have the same chronological age. They're all 15 years of age. But they don't look the same and they aren't the same. This boy has not yet started adolescence. He's pre-adolescent. And this boy is post-adolescent. He's a young adult. Still 15, young adult. And this boy is in the middle, just going through peak-height velocity. So there's a clear distinction between chronological age on one hand and maturational age on another. This is a little bit extreme, but there is this difference between maturational and chronological status. Now, early maturing boys are likely to have an advantage in sport, since they'll be physically larger and stronger in most dimensions, irrespective of ability. And late maturing boys, on the other hand, will be disadvantaged largely because they're smaller. And as a schoolmaster, a former schoolmaster, I've even noticed that myself. Boys have come to me and say, "Why am I not playing?" Because I'm better than he is. And I've had to make some kind of excuse to say, "You're playing next week," or something like that. Okay? So late maturing boys, on the other hand, will be disadvantaged because they're smaller. Nevertheless, late maturing boys may eventually overtake early maturing boys, and their ability, therefore, recognised for all to see. So lack of size per se, therefore, is not necessarily an indicator of lack of ability. Take Messi, Barcelona. He's never been any taller than he is now. And I'm taller than Messi. And he's been designated the best soccer player in the world for 3 consecutive years. So lack of size does not necessarily indicate a lack of ability. This is a radiograph of 2 boys, both aged 14 years. In skeletal age, or bone age, it doesn't matter what you call it really, this boy is 16. So he's 2 years ahead of his chronological age. This boy is 12 years. So he's 2 years delayed in terms of his chronological age. Okay? Now you can see that the round bones of the wrist there, this is the left hand, it's a standard position, a left hand, okay? Those are all mature. It's not a question of size, it's a question of developmental status. That's what's important. So those round bones are fine. The metacarpals are fine. And most of the phalanges are fine, except the terminal phalanges. They're not mature. They need further ossification yet. And I checked this out myself only the other week. If you look at the radius and the ulna, the cap started, but it's not fused yet. It's not fused with the epiphysis. And the fusion line is still there. And until the fusion line goes and the caps are complete, then it won't be mature. And it was fixed at stage H, and there was only one stage left, stage I. Then it became mature. So this young boy should be mature in 6 or 12 months, something like that. The other boy, the 12-year-old boy, his bones are less well developed. You can see the fusion is starting to begin between the epiphysis and the diaphysis in both the radius and the ulna. Round bones aren't developed at all either, nor are the metacarpals. And the dark areas on the hand are where the bones need ossification. So you can see there's a lot of ossification required before this boy becomes a young man. So bone age and skeletal age is the best technique to measure maturation. Now, we didn't have facilities for measuring radiographs, so what we had to do was use Tanner's secondary sexual characteristic age scale, or pubertal development, and each child was given, when he came into the lab, was given a set of photographic standards to indicate pubertal development, and the child was asked to indicate at what stage he belonged. This was done, as procedure was carried out privately in the changing room, in the laboratory, whilst boys changed into their kit in order to proceed to the next series of tests. And these are the values which occur. This is the active group, the soccer group. This is the control group. And you'll notice that the control group reaches each pH stage slightly earlier than the active group. 13.2, 13.3, 13.8, 14.2, 14.2, 14.7, 14.8, 15. And the same is also true if you look at the control group on the UK mean. But they weren't significantly different. When a whole analysis was done, there were no differences between groups at any age. So that's maturation and the importance of maturation. These are somatotypes. Soma meaning body, types, body types. The shape of the body. Okay? The responsibility for somatotypes was an American, W.H. Sheldon. He was given the responsibility really for the concept of the somatotype. And the somatotype is a three-dimensional classification, a three-dimensional system for the classification of physique. It considers shape, it doesn't consider size. Size is irrelevant for somatotype. And the individual components are endomorphic, mesomorphic, and ectomorphic. They're always given in that order, and each component is rated on a scale, a Sheldonian scale, from 1, which is the minimal, to 7, which is the maximum. And endomorphic refers to a smoothness and roundness of the body with little or no muscle definition. There's a predominant abdomen and weak arms and legs. On the other hand, mesomorphy is a squareness, a hardness, a ruggedness of the body. A classical Hercules. And ectomorphy refers to linearity and fragility. It's a little amount of fat and a little amount of muscle. It's tall and thin. And so somatotypes like these, which are Sheldonian somatotypes, are assessed subjectively. And then they're put on Sheldon's chart, and you can look at the distribution of different kinds of individuals, or compare yours with theirs, and so on. Now, Sheldon was a very difficult person to work for. He worked with a woman called Barbara Honeyman-Heath, who was an authority in somatotyping. But they disagreed over many matters. Okay, he thought, for example, that the somatotype couldn't change. Therefore, it must be genetic. And he was wrong. He thought that the values from 1 to 7 would cover all population groups. And they couldn't, because Honeyman-Heath had been to South Africa, and she brought back some photographs showing athletes, not athletes, but even normal individuals with a greater value than 7 in the second component, mesomorphy. And so eventually they fell out. And she went to work with a person called Lindsay Carter, who worked in this field. And Heath and Carter, between them, redesigned the system and came up with what they call an anthropometric somatotype. It used anthropometric measurements only. So the system, in a sense, became to some extent more objective, only more objective, because it wasn't wholly objective in the first place. The components were still referred to as endomorphic, mesomorphic, ectomorphic, although they were redefined in a more satisfactory way. And theoretically, it had an open-ended scale. It wasn't closed, except it didn't go farther than 16, which was a high value. Okay? And all subjects in our study were assessed using an anthropometric somatotype. Now, these somatotypes are some of our former students. I don't know whether you can recognise them or not, because it would help me, because I don't recognise them all either. There's only one of them I know. They're rugby players, and in order of playing position, scrum half. If I didn't tell you what they were, most of the rugby players would know what they were. Scrum half, outside half, centre and wing. And of course the wing is the most notable of all players. Played for Wales for lots and lots of years. And he was a British Lion. And he played for lots of the representative teams for rugby. And he was a Welsh sprinter too. And he was a former student. And I used to teach him gymnasts. And again, you see, you look at them from another point of view as well to make a comparison between endomorphy, mesomorphy and ectomorphy. Ideally, it would be better to have an anthropometric somatotype and have a photoscopic somatotype at the same time, because you can get something from one and something from the other. And your profile would then be much better at that point. So this is the mean somatotype now. This is the anthropometric somatotype. These are the units in measurement, and these again are years from peak height velocity. Okay, and we're looking across adolescence now. Okay, and looking at each individual component. So we've got ectomorphy, which tends to decline a little bit, mesomorphy, which tends to decline a little bit, and endomorphy, which tends to increase a little bit. Now we were using now a 13-point scale. Originally it was 7, but if you split 7 into half units, then you get 13 points. And you can use half-point scales, which we did. Okay? And so it was originally a 2.5, a 3.5, a 4.5. And if you round that up, of course, then you get a 3, 4, 5. So the mean somatotype for the control group was 3 in endomorphy, 4 in mesomorphy, and 5 in ectomorphy. Okay? This is the figures for the active group. Okay? It's quite unequivocal. It's unequivocal. Endomorphy, a slight decline. Okay? And mesomorphy and ectomorphy, pretty much the same all the way through adolescence. And that's a straightforward 2, 4, 4. 2 in endomorphy, 4 in each of the other 2 components. And this is Sheldon's chart. Okay? There's our active group at 2, 4, 4, our control group at 3, 4, 5. There's nothing spectacular about them at all. It's a central group. There's lots of people who have those types of somatotype. Okay? These are the extremes, endomorphy, 7, 1, 1. You'll get all your obese people down here. Your mesomorphs will be your gymnasts, your wrestlers, your boxers, your weightlifters, and all those kind of people you will find up in this end here. You won't find many athletes in ectomorphy. Maybe some long distance runners, maybe 1 or 2 high jumpers and people like that. Okay? And the midpoint is a 4, 4, 4. Now, a number of years ago, I don't know whether you've read the book, Tanner's book, The Physique of the Olympic Athlete. He, at Rome, assessed the athletes, track and field athletes, and they came within those 3 segments. All of them within those 3 segments. Now, a few years earlier, he had done the students at Loughborough, the PE students at Loughborough, and they were strong also athletically in their time. And they also had those 3 segments. They belonged to those 3 segments. And when I did the Cardiff boys, they were essentially these 3 segments, except there wasn't so many in this area, okay, because this is endomorphy, and that's what they didn't want, of course. There was a tail in this area, but essentially they came from those 2 areas, soccer players and rugby players. Okay. So it depends what sport you have and play, what kind of shape, or your shape dictates, in a sense, what game you play. Okay. So overall, somatotypes in the control group and the active group were fairly stable during adolescence. A 2, 4, 4, in my view, is a more robust somatotype for a games player compared to a 3, 4, 5, simply because it has less endomorphy and less ectomorphy. Now, this takes us back to Archimedes, okay, and his contribution to the 2-component model of body composition. King Hiram, who was king at the time, had been victorious in his battles against his enemies. And he decided he would pay homage to the gods by dedicating the crown to them. It would be made from gold and it would be kept in the temple. However, it was reported subsequently that some of the gold was being withheld and replaced by silver. And the contents of the crown couldn't be separated, they couldn't be disintegrated because of the crown's religious significance. So the matter was referred to Archimedes. Okay? And it was when Archimedes observed, when he entered the slipper bath, that the water overflowed. And he concluded that the volume of water displaced was equal to the volume of his body when it was immersed in water. That's point number one. And point number one, he also deduced that body volume could be determined by weighing the subject underwater and measuring the loss of weight while underwater. That's the principle of densitometry, or hydrostatic weighing. Okay? Now, Archimedes went about his experiments. He measured the volume of the weight of the crown, the same weight of silver, and the same weight of gold. He did that by water displacement. And he found that the crown caused more water to overflow than the gold, but less than the silver, indicating a mixture of the two components. And subsequently, it was found that the crown was calculated to have adulterated by 25% silver. And Archimedes confirmed that finding when he did the same experiment when he was using hydrostatic weighing. Okay? Now, so what we're doing really is we're transferring silver and gold to fat and fat-free mass. That's where we're going now. Okay? Because it's a two-component model. Silver and gold was a two-component model. And fat-free mass is a two-component model. And so we're following the same principle. So this tank is filled to about 2/3 full, 36 degrees centigrade. Okay? The subject climbs onto the reception area and puts on a belt where we know the weight of the belt. Okay? He goes up the ladder and there's a seat attached there and he sits on the seat. We give him a nose clip as well. Okay? So his head is above the water. Okay? And then we give him a number of preliminary trials. Breathing in and breathing out maximally. Breathing in and then breathing out maximally. And when he's breathed out maximally, his head, when he's finished, he closes his mouth and his head goes gently under the water and he remains perfectly still. Perfectly still. And at that point, we can determine the value from the scale at the top there. Okay? And we needed 3 satisfactory trials. That's all, 3 satisfactory trials. And once they'd done that once or twice, you could get those quite easily. Okay? The technical error measurement was 30 grams, coefficient of variation 1%. Now, after breathing out maximally, of course, there is still a certain amount of air left in the lungs. Okay? That's residual volume. And that has to be measured, and it has to be subtracted from underwater weight, because it has contributed to underwater weight. So after they've done their underwater weighing, then we measure their residual volume while they're in the tank. And you can see here, there's the valve, nose clip. That's the beginning of the valve, the rebreathing valve. And that's filled with a known volume of medical oxygen. Okay? So the subject inhales and exhales 3 times from a rebreathing bladder. Okay? And they do that just 3 times. In, out, in, out, in, and out maximum. And we switch it over. So the bag is closed. And so we do 2 bladders. We do two bladders. And then we find the mean value. And we can collect and measure the residual volume from those trials. Okay? Now what that brings us to then is the calculation that was used for determining total body fat. Okay? Using exactly the same principle that Archimedes made. We know all about this because we've done it. What we're after is body density, which is equal to body mass, which we've measured, and volume is equal to the mass in air minus the mass in water divided by the density of water. which we can get because we know the temperature of the water. Okay? And then we've measured residual volume in the meantime, and we take that away, and we get a value for body density. There's just two other components required. One is the density of fat, 0.9, and the other the density of fat-free mass, 1.085. And that value refers to children, because children are not chemically mature at adolescence. They like bone mineral, they like protein, they like total body water. Okay? And so the equation for children is percentage total body fat equals 5.28 divided by density, which we've worked out, minus 4.86 times 100. That will give us percentage total body fat. The remainder is fat-free mass, muscle, bone, cartilage, all the internal organs, and so on. Okay? And if you take that away from 100, then you can get percentage fat-free mass. These are now the distance velocity curves for fat-free mass. Okay? This is fat-free mass, years from peak height velocity. Fat-free mass in kilograms per year, years from peak height velocity. Now again, you can see that the sedentary group are slightly, have a greater fat-free mass, again up to about minus 0.5 years peak height velocity. And then the fat-free mass continues to increase more rapidly. And that's a consequence of these much larger velocities in the velocity curve for fat-free mass. Okay? And again, there is no significant difference, surprisingly, because there's quite a gap between those two control and active groups. Okay? And if you look at the velocities, velocity occurs at minus 0.5 and at minus 0.85. That's where the active group crosses over the control group and becomes much larger. So once you get the velocity group actually dictating what the shape of the distance curve will be. Now, we would normally expect active boys to have greater amounts of fat-free mass. The reasons for this could be the effect of playing competitive soccer weekly, training weekly, and increased growth of the adolescent sport. Or more likely a combination of all those events. This is the distance curve for fat mass as a percentage, okay? And you can see that there is a decline in total body fat in both groups, control and active. From there to there is about 6%, and from there to there is about 6%. So there's a 6% loss during adolescence in young males, adolescent males. This point here, from minus 1 to minus 2, is the tail end of the pre-adolescent fat wave. Youngsters have a fat wave before they have a fat loss. And that's where it's finishing in this group. It's the tail end of that, okay? And then it declines. This position here is a bit more speculative. Okay? It could be, some children have a post-adolescent fat wave. Some children, not all children, but some children do. And that may be the beginning, I just say that. But the numbers in there are also smaller than the other numbers, so that may be a problem as well. So I'm not quite sure really what that is, okay? So when we look at the velocity curve, you forget that value because that's what makes that position there. Now, the velocity curve for total body fat. The other thing to say about fat is it's the most difficult of all the tissues to interpret because it varies according to site. You know, what part of the body you take the measurement. Okay. Now, the velocity curve for total body fat, all the lines, all the dots below 0 are negative. Negative 1, negative 2, negative 3. So a fat loss means a negative value. Okay. A loss of fat indicated by a negative value. So fat loss is lost in both groups, control and active. Okay? And the nadir of fat loss, the lowest point of fat loss in both groups, is about 3% per year. In the sedentary group, it occurs just before peak height velocity. And in the active group, it occurs just after peak height velocity. So they're associated with peak height velocity. And peak height velocity occurs at 14.2, and peak fat mass velocity also occurs at 14.2. So while you've got a peak in height, you've also got a trough in fat. This, therefore, is the summary. Peak height velocity we used at 14.2. And at plus 2 years peak height velocity, the active boys were taller and the active boys were heavier. Taller and heavier at plus 2 years peak height velocity. Okay. Both the active and the control groups in pubertal development was pretty normal. And the somatotypes across adolescence were also pretty normal. Okay. The control group had a somatotype of 345 and the active group one of 244. And the active group had a larger fat-free mass than the control group. Okay. And body fat, as expected, decreased in both active and control groups, but by the order of about 6% in the distance curve and about 3% in the velocity curve. Okay? So there was a decrease in body fat. And at that point, I'd like to say thank you very much for your attention.